So, hi. So I'll be doing um tank levels and finding what the height will be at certain levels of a tank, and I'll be bringing that into coding as well to try and simulate what specific heights would be at certain like tendencies and areas of like the tank as well. So to be able to get what we're doing today, I'll need to derive what we're working on today. So the task is basically finding what will where we'll get the equation that we're looking for in this case. So the tank equation originates from the from Bernoulli's equation. Bernoulli's equation is the change in density over pressure plus gravity multiplied by the change in height plus v squared minus v squared final minus v squared initial divided by 2. So when it's in steady state, this will cancel out as well as this. So it will be equal to 0 in steady state. So we'll be doing g z. This is the same thing as the change in height. So I'll correct that. So that'll be h. So even in this case as well, this will cancel out in the process of being in steady states. So we'll have the final, let me just make this clear. V squared final divided by 2 is equals to GH. So now we'll cross multiply. V is equals to 2GH. So for that V, square root of 2GH. Okay. So now we're dealing with tanks. So as one, we're dealing with 3 tanks in total. So as one is entering, the remaining amount is entering another one as well. Then the final amount is entering another one as well. So we'll say this is Qn. This is the amount that's entering at first. So then we'll name this one that's leaving here Q1 because it's coming from tank 1. Then the one that's leaving from here will be Q2. Then the one that's leaving from the third tank will be Q3. Okay. So the pressure in basically is the area, that area AH multiplied by the volume of the liquid itself. Sorry, is multiplied by that speed, the speed at which it moves throughout the tank. No volume, speed. My bad. So this, you now plug it into this as well. So that'll be P equals to AH multiplied by 2GH. Okay. And that pressure is the same as what's coming out. So This is equals to Q out. That's what equals to coming out of the tank itself. So take note, we're going to be using this equation for most of this, but I'm going to show you as a, let me start from here, dv dt is equals to a dh dt. And the area must vary by like the change in height over time. That's equals to what's coming in minus what's coming out. So that means a dh dt is equals to, sorry, dh dt is equals to q in minus q out over a. And what do we know q out as? This. So that means q in minus ah multiplied by 2gh square root divided by a will give you your dh dt. Now, when it's in steady state, that dh dt will go to 0. So dh dt will go to 0. So it will be equals to this. And that dh is basically was like the difference in height per se over a certain period of time. So we'll use this, we'll differentiate this. This will give us a way to find the initial height at steady state, which is this. So we'll make this h itself this of the formula. So 0 is equals to qn minus ah multiplied by 2gh divided by a. So this would be ah. I'm just multiplying ah multiplied by square root of 2gh is equals to qn. So we divide both sides by ah, so that will be 2gh is equals to qn minus ah divided by ah. So you square both sides to take away the square root. So that will be 2gh is equals to qn ah squared. You now divide both sides by 2g, and that will give you what your h naught will be. So that will be qn divided by ah squared divided by 2g. And that is how we get the height at steady state, which is like the beginning height from the beginning. Okay. So now we'll go into the coding side of things. Okay. So let me leave from here. So now we'll go to the Kugel Colab side of things. So now we import the functions that we'll be using throughout this time. So we start from the import numpy as MP, which will help with the functions. Then the SciPy integrate with SolveIVP, which will help with solving differential equations, as well as the subplots, because we'll be creating graphs to create the simulations to see where it's changing in general. So let's run that. Okay, so now we can start defining our products, our like variables. So AC is equals to 0 and is equals to 1. AH is equals to 0.05. Sorry. Then we have Q in a steady state, which is 0.75. Then we have Q in itself, which is, so Q in is 1. Then they said the Q in is 0.75 times what Q a steady state would be. Then we can say our area will be 20 meters per meter squared. Then G, acceleration due to gravity, is 9.8. Then the H initial, which we just solved, will create like a formula for that, which we solved from the previous equation. So that will be Qn divided by AH squared divided by 2 times G. Let me just remove these extra brackets. So now we have then T as well, T end, which is what we'll put like as the final limit, really. We'll put at like 2000. So let's go on down. So now let's define the functions. The define RHS is what we'll use as we're solving differential equations. So we'll use T at those specific times, we'll get the height. Okay. So now we'll define the RH, the right-hand side. We'll use the equation, the dH dt, which is the change in height over a specific period. dH dt is equals to, we'll say from the previous equation as well, we'll use Q in minus Q out, and Q out was that AH multiplied by NP square root of 2 times G times H. Then now divided by the area. So now we'll return dH dt. We've defined that now. So now let's start planning for the plots. So that region, we'll put it as NP length space, which will give us like a range of where to start and how the separations will be for each one. So sorry, right hand side 0. Then we'll do the heights. Then we'll do the dense output to give you a clearer view of what we're solving. True. Then we'll put the res, which will give us the results as solve IVP, which is the function I will be using to solve. Sorry, I mixed it up. Taking this is meant to be in this, then 0, which this is like the range, like I said earlier. So we do 500, every 500 units until it reaches 2000. So then the res will solve the differential equations of the right-hand side from the 0 to the the end, which is 2000 seconds for that height. Then I'll print out res. Then now, as we can see for each, it shows at each time what the height will be. So those t values are what the times will be, and those y values shows what the height will be at those specific times as well. So now that we've already solved that, so now let's get to where we'll be working on 3 tanks. Okay. So now we define right hand side 3 tanks. And this time we'll be using V as the, but there's a reason why I'm using V in this case. So before that, let me include the the values that we're working on in this case. So here it says we're working on the set point. They said the set point increases by 10% every time. So we'll do 1.1, which is like 10% increase multiplied by the heights at steady states. Then they said the Kc value, we should look for that as well. So I'll start at something about 0.175 to see what Kc values would be to see where it oscillates perpetually. So we define those values as well. So now let's define those heights as vectors. So I use that V to show like those 3 heights. We'll define them as vectors. Okay. So now we define it as vectors. Now we'll find what the error may be as we're checking the set points from here and the set points of this as well. So now after we found the errors, we'll find Qn depending on what those Kc values will be. So we do Kc multiplied by the error plus the steady state, like inlet flow. So now we've defined what they will be. So let's put together the formula for each flow from each tank. Like I showed earlier, it goes from the in down to what Q1 will be to Q2 and to finally to Q3 and what will come out from Q3. So Q1 is equals to that AH multiplied by MP square root of 2 times G times H1 in this case, because we're looking at the 3 different tags. They all have 3 different heights. So I'll simply just copy that on to. So I'll just adjust according to that Q3, H2, H3. So now we'll return what the what the height will be as it goes through those different stages. So np.array. So this will show for the 3 different heights. The reason why we didn't use an np array in the previous one was because we were just looking at the 1 tank. Now we're looking at all 3 tanks as they flow through each other. So now we'll use the flow in minus the flow out. So from the first tank, it started coming in from Q in. Then what was leaving was Q1. Then we divide that by A. Next thing, we have Q1 minus the flow of Q2 divided by A. After that, we have the flow from Q2 minus Q3 divided by A. So this is what's giving us what the flows will be as we're leaving from each, as we're going down from each tank, like I showed in earlier in the video, as it was going down one by one. So now we return that. So we're able to run. So now let's start focusing on what the plots will be. T plots. Okay, so first let's define a new T end, what the final time will be over time. So let's start with 30 seconds. So T plot will be equals to, like I said, that MP lane space is what creates like a range and what like values will be going in. So we'll start from the beginning, final T end in like a rational of 500. So every 500 until it reaches 30,000. Then I'll also put together the res. So that res will be equals to, we'll use that solve IVP again. We're solving for the right-hand side, like I said, but now we're focusing on the three tanks. The three tanks, then we'll do the T, so the 0 and the T end again. So then we'll do, now that like I said, we're focusing on all three as it goes on from one tank to the other tank. We'll focus on that as well. So that's why we put an array. Sorry. So H0 for all three tanks. So, sorry. So now we'll be focusing on the dense outputs again. So like I said, we'll put true. Now we'll do something different called the method. We'll use radar, which is like a very effective way of calculating like long calculations like this. So we'll close the brackets. Let's scroll down. Let me run it. Let's try it for res. I will see how it will run. So yeah, it's showing how each value be at each time, what the height will be. So now we've been able to clarify, okay, it's running. We delete the. So now it's time to make plots. So fig, sorry, fig is equals to make subplots. Okay, now we'll start making the subplots. Fig dot I scatter. So our X will be the T plots. Our Y will be the H1 plots. Then, then we'll name it tac one. Let me put this tac one. But notice how I didn't put the, I didn't define those, the H1 plots. So let me go back in and define them. So we do the same thing. Let's go to let's see. B is not defined. Of course, the resolution T plots. So now get defined. So let's just we'll copy and paste this for the three different ones. Okay, so for so top one, then this T plot H2 plot for the second tag. Same thing again, H3 plots for tag 3. So now we'll try and scale it out. So fig dot date layout. So we'll put the width on the graph at 600. We'll put the height of the graph as 400. Then let's put the template as lovely. Just give it like a dark effect. It's not by force to put it totally dark, but just as an effect. So we were able to see that it oscillates a little bit, but we can always adjust the KC values. So let's try 0 0.200. Shift enter, shift enter, shift enter. Okay, it's oscillating a bit more. Let me increase that to 0.25. Oscillates a little bit as well. Let me try 0.275. Okay, we can see the oscillations are increasing a little bit. Let's try. Let's try and see what to say at 0.300. So yeah, now it's increasing and it's giving weird values. So I feel like we can leave the KC values. We'll say the KC values oscillates perpetually at like at about 0.275. Zero point 225. Let's see. Yeah, let's start from the beginning. Yeah, we found the issue. So we put this right here. Now you can see that that caused a mistake. So let's try that again. So now the oscillations are back. So let me try that 0.275 again. Okay. So we'll just leave it at like 0.2235. Yeah. So the the best KC value will leave it at about 0.235. So yeah, thank you and hope you have a wonderful rest of your day.